Okay, these are the answers to the orange workbook, pages 120 to 121, questions 1 through 12. So we're going to start by, first we reviewed the blue workbook, now we're going to review the orange workbook. And we are going to start by answering question number 1. In a true solution, the dissolved particles are, well, in a solution, when I have a salt completely dissolved into water, and what type of solution? What is solution? It's a homogeneous mixture. That means we cannot see the different parts. We cannot see. Therefore, they're not visible in the eye. When the solute, the salt dissolves, the particles are so tiny small that they will never settle out on standing. What does that mean? If I take a bottle of water and I add salt, the salt will dissolve. And if I close that bottle, it doesn't matter how long that bottle of salt water stays. The salt will never fall on the bottom. It's always going to be dissolved throughout the water. I don't have to shake it to dissolve, to mix the salt molecules that they're dissolved. They're so small that they will not settle out on standing. And also because they're so small, they cannot be removed by filtration. Try it at home. Take water, add some salt, dissolve it. Pass it through a coffee filter. That's filtration, passing the salt water through a coffee filter. Will the filter separate the dissolved salt from the water? No, it's not. And well, the dissolved particles, they're not always solid. It can be a gas dissolved or carbon dioxide dissolved in water. It can be a liquid, alcohol dissolved in water. They're not always solids. Salt water, well, salt and water, they're a mixture. They're not a compound. If it's a physical mixture. And because it's a mixture, you need to remember that a mixture is combined in a variable composition. What does that mean? I can have 1 tablespoon of salt, 2 tablespoons of salt. It doesn't really matter. It's still going to be a mixture of salt water. And it's always going to have a variable composition. The compound is with fixed composition. The mixture, the composition varies. In an aqueous solution, potassium chloride, the solute is the KCl. So when I have KCl, aqueous, the KCl solid is the solute. So when I put that into water, what happens to this ionic compound? It breaks down to K plus and Cl minus. So that is your solute. This one is your solvent. And you're not going to only have K plus or Cl minus. You're going to have both because it's going to break down into water. Which sample of matter is a mixture? Well, this is a substance that's a compound. It's a solid. This is a compound. It's a solid. This is a compound. It's a liquid. So therefore, the answer is aqueous. Whenever we have a mixture, what are we going to see? AQ, aqueous. Let's go on number 5. Most ionic substances are soluble in water because, well, that comes, the like dissolves like. So what does that mean? Polar dissolves polar. So if it's ionic, whenever it's ionic, I want you to know that it's a polar compound. That comes, we remember that from bonding. Ionic substances are polar. And what do we know water is also? Polar. So most ionic substances are soluble. If they're soluble, they have to have the similar polarity. Therefore, if ionic is polar, we know water, you're always going to remember, if there is something that you remember about water, water is a polar molecule. So ionic substances are soluble in water because water molecules are polar. If I have an aqueous solution of copper sulfate and it's poured, now if I have a solution and it passes through the filter paper. What's going to pass through? Well, the solution of copper sulfate and the water. So both the solvent and the solute. Which one is my solvent? The water. Which one is my solute? Copper sulfate. Why? Whenever I have a solution, both the solvent and the solute will pass. Filter will not be able to separate the dissolved salt from the water. You will have to boil off the water so that you can get the solute back. Let's go to number 7. Like dissolves like. Nonpolar solvents will most likely dissolve solids that are, well, nonpolar dissolves nonpolar. So nonpolar solvents will dissolve nonpolar, dissolve nonpolar. Like dissolves like. Ionic, what do we say? Ionic are polar. Covalent, we are going to say they're nonpolar. Metallic and colored don't make any sense. So nonpolar, dissolve nonpolar. So nonpolar solvents will dissolve covalent nonpolar solids. As the temperature increases the solubility of all gases in water, let's say we forgot how to go about this. Let's go ahead and go to this reference table. And let's go to table G. Let me just, okay, what do we say? Let's go back to our question. As the temperature increases, the solubility of all gases in water, what did we say? We said the gases are 3. As the temperature increases, the solubility of all gases decreases. So let's just, okay, so as the temperature increases, solubility of all the gases decreases. Which ones are your gases? There are only 3. HCl, NH3, and SO2. So you're going to remember that there are only 3 gases. As the temperature increases, the solubility of the gases decreases. So we will clear these drawings and we're going to see. So as the temperature rises, the solubility of all gases in water decreases. A decrease in pressure has the greatest effect on a solution that contains. Now, pressure affects gases only. So I'm going to eliminate liquid in a liquid, solid in a liquid, solid in a liquid, and the answer is gas in a liquid. So a decrease in pressure has the greatest effect on gases. Therefore, gas in a liquid. Number 10, we have NaCl. We talked about it on the blue workbook homework. NaCl is an ionic compound. If it's ionic, it breaks down to the ions. What are the ions? Na plus and Cl minus. What do I know about water? Water is polar. Okay? Remember which one? Which one is more electronegative? Oxygen. That's why it has a partial negative and a partial positive. Opposites attract. So which one is going to be attracted to the negative, the positive? Which one is the positive? The hydrogen. So therefore, it's going to orient itself like this. The hydrogen is going to be oriented. And what's going to be attracted to the positive? The negative. Therefore, the water is going to orient. Which one is the negative? Oxygen. Let's see. The sodium is going to be attracted to the oxygen. That makes sense. That doesn't. That makes sense. That doesn't. The chlorine, the chloride, is going to be attracted to the hydrogen. That makes sense, but this doesn't. Therefore, the answer is choice number 1. I know this is not a good picture, but let's go back. What happens when sodium chloride is dissolved in water? Well, it's what we did before, okay? What did we say? What happens when sodium chloride is dissolved in water? What did we say? Na plus. Which one is then attracted to the negative? Which one is the negative, the most electronegative? The oxygen. How about chloride ion? If oxygen is negative, then hydrogen is going to be attracted because water is polar. Partial negative, partial positive, partial positive. And you see the hydrogen looks like a positive kind of. So we're going to see, it says the chloride are going to be attracted to the oxygen. No, the chloride are going to be attracted to the hydrogen. Therefore, that doesn't make sense. So the chloride ions are attracted to the hydrogen atoms of the water. Yes, let's make sure the other ones are wrong. The sodium ions are attracted to the hydrogen. No, the sodium ions are attracted to the oxygen. And no, there are attractions involved. The crystal doesn't just fall apart. What causes it to fall apart is the attractions between the water and the ions. Let's go to question number 12. And the question number 12 says 2 grams of potassium chloride are completely dissolved. Completely, that's the word, completely dissolved. Underline that. In a sample of water in a beaker. This solution, the moment you have a solution, what do you always have? A homogeneous mixture. I hope it was helpful. Review. I would do first my blue workbook questions 53 to 55, and then I would do this one after I read these pages of the orange workbook.